In today's lesson, we're going to continue working on relations. The way two quantities are related is a relationship, and we call that graph or that equation, that rule, a relation, right? So y is equal to the square of x is a relation. Relations can be further categorized into functions if they have the quality that when you insert a number into x, or you into your rule, for example, if I put 3 into this rule, the output produces only one value for that input. So when I put in 3, I get 9. I don't get 3, or when I input 3, I don't get 9 or 5, etc. So a function is a special type of relationship in which there is only one output for every input. Okay, so sometimes the best way to identify what something is to look at what it isn't. So let's look over here at non-functions, relationships that are not functions, right? So in this particular one in the table of values down here, I can see that I put in 6, and when I put in 6, I got 10. But when I put in 6, I also got 15. So because I get two different values, right? So if I put something in and I get two different values for the same input, that's what makes it not a function. Same thing over here. When I put in 12, I get 10 or 14, so it's not a function. Down here, when I put in 3, I get 10, 15, or 20, so not a function. So looking at your table of values or your ordered pairs, if you have a repeating value for x and the outputs are different, then you know it's not a function. If I look at a graph, I know that when 2 points line up vertically, that they share the same x. And so if 2 points line up vertically, then it's the same thing as my table of values. If this was negative 2x here and this was negative 2x in this point, well, I can tell because they're at different heights that the y values are different. Perhaps that one's 5 and perhaps that one's 1. So because 2 points on my relationship line up vertically, it is not a function. And then the same thing over here, that same rule, right? If I draw that line through those 2 points, I know that they line up vertically, therefore it's not a function. So let's go look at examples of functions, okay? So if I look at this graph, no 2 points line up vertically, therefore it's a function. Same thing here. As I go across, all these points do not have another point that vertically lies identical above it on the graph. So this is a function, is a function. If I look at my table of values, do you notice all my x values are different? Therefore, each x value is going to have its own unique y value, so it is a function. Okay? If you look at the second table of values, 11 is producing 3. It's not producing anything else. 21 is producing 3. It's not producing anything else. 31 is producing 3. It's not producing anything else. Or I could write it like this in my mapping, right? 3 is my output. They all produce 3, but that's okay. It's still a function because 11 only has one output. 21 only has one output. 31 only has one output. I don't care that they all share the same output. I only care that when I input something into my rule, I'm only getting one thing out. So your y's can repeat for different x's. It's just your x's can't be the same for different y's. So you have to be careful with that part of the rule. Okay, so let's practice that. So in review, what did I say? When you have a table of values or ordered pairs and you want to know if it's a function or not, check to see which relation has a domain value associated with more than one range. Okay? Or, for example, in summary, if one x value produces two different y values. So I go through this one, 5, 6, negative 5, 2, 6. So this is where I'm going to focus. 6 is producing 7 or 8. Right? So no, this is not a function because of that. When I look over here, 3, 2, 4, negative 3. Oh, all my x's are different, therefore this is a function. I don't really care that 3 is producing 3 and 2 is producing 3. I just care that all my x's are different, So each x has its own single output. In my mapping strategy, A is producing P, B is producing Q, C is producing P. I can see that A only has one arrow from it, B only has one arrow, and C only has one arrow. Therefore, it is a function. Whereas in this one, A has two arrows, A is producing P or Q, therefore this is not a function. Okay, so using points, ordered pairs, mapping, table of values, you can see if it's a function or not. If we have a graph, remember what I said with a graph, if 2 points on a graph line up vertically, it is not a function. We call that a vertical line test, because if 2 points line up vertically, then you can draw a vertical line through it. So if a vertical line crosses through the graph, it is not a function, right? So at any point of a vertical line passes through a graph, it is not a function. If I was to draw vertical lines here, none of them would go through the graph twice, so this is a function, right? All linear relationships are functions unless it's a vertical line, right? So if it's linear, yes, it's a function, right? Because every input only has one output. The other thing we're going to learn today is a special way of writing functions. So remember, all linear relationships are functions. So another way to write a function is instead of writing y, we are going to write f of x. F of x is just a fancy way of writing y, right? F of x just means this is the output for this particular input. So in the brackets you put what you're using for x, right? So f of 5 means that x is 5. In the rule that follows, I'm going to, so 3x minus 2 is the rule, and the rule that follows, I'm going to insert 5 in place of x. And then you can evaluate it. 15 minus 2 is 13. Oh, when I insert 5 into my equation, I get 13, right? F of 5 is a fancy way of writing y when x is 5, right? It just gives you more information. Rather than just writing y, you're writing what x you're choosing. Okay, or what the input is. If you just wrote x, it would be this is y when your input is x. Okay, and so we can use lots of different letters. F is used most common for function. You can use g of x, h of x. There's anything you can use, right? D of x, right? D of t, right? Distance is a function of time. Okay. So if I give you a function, g of x equals 5 minus 3x, you could evaluate g of 4. G of 4 just means let x be 4. So when you see your equation, you replace x with 4 and you evaluate, following your order of operations, and you would get your final answer. Oops, sorry, 7. And then over here, you're inserting negative 2 in place of x. So you would replace the x with negative 2. And be careful, a negative times a negative is a positive. And you would evaluate using your order of operations. This means when x is negative 2, my output, my g of negative 2, which I can also call y, is 11. That is now a point I could put on my graph. Left 2, up 11. I can use fractions, right? You can use fractions, you can use decimals for your input. Okay, so when I multiply 3 times 2 over 3, the 3's cancel, right? When you're multiplying fractions. And then you can evaluate. Sometimes when I give you a function like f of x equals 2x minus 3, I can give you what f of x equals. F of x is negative 1. Well, this does not mean that x is negative 1. This means that f of x is negative 1. And remember, f of x is a fancy way of writing y. So it means my output is negative 1. This is my output, not my input. So I'm going to replace my output with negative 1. And I'm going to work backwards using my algebra skills, right? I'm going to add 3 to both sides. And I'm going to use my algebra skills, divide both sides by 2, to figure out the value of x. Oh, when I input 1 into this function, I get -1, right? So when x is 1, I get -1. So making sure you understand, when am I giving you the input and when am I giving you the output? If I'm giving you f of x, I'm giving you y. I'm giving you what you get, the output. And so you have to put that in place of f of x, right? So I'm using the same formula, so I would put 7 in place of f of x, and 7 equals 2x minus 3, so I would do the same steps. Add 3 to both sides, clean it up, divide both sides by 2, and I would get 5 is equal to x. All right, that means when I input 5, I get 7. And instead of y, I can always replace y with f of x. They are the same thing. When x is 5, f of x is 7. I could do the same thing on a graph, right? So for example, if this is f of x, I don't give you the rule, but I give you the graph. And remember, the graph of a function is made up of a bunch of points that work in my rule. So I don't know the rule, but I know a bunch of input-outputs that work, right? So if I ask for f of 3, what am I asking for? I'm saying when x is 3, this time I'm giving you the x, I want to know the output. I want to know what does y equal. So I go to my graph and I find where x is 3. X is 3 right here. So this point is 3, 0. So when x is 3, my y is 0. So I get 0 for y. Whereas f of -1 means x is -1. So let's find where x is -1. I go left 1 and I go up to my graph. Oh, this is where x is -1. And when I plug in -1 for x, I'm getting, right? When I plug in -1 for x, I'm getting 8. So f of -1 is 8. So when I give you the number in the brackets, I'm giving you the input. When I give you the number, what f of x equals, I'm giving you the output, or I'm giving you the y value. Right? So if the y value is 0, which I've done over here already, the y value is 0, you now know the x value. Oh, x is 3 to get 0. Okay, let's try that one. When am I getting -4? Well, this is your y value. So you have to now go on your y-axis to -4. Okay, so I'm on my y-axis, so I go across to my graph. So when y is -4, I need to insert 5. Oh, 5 produces -4. So now I know x is 5. Okay, so that's function notation.